Hello, my name is Gala and I'll be sharing my answer QSRA research done under the supervision of Dr. Liscouët-Hanke. This project consists of a tool development for conceptual design of hybrid electric aircraft, also called a hybrid electric sizing tool. The objectives of the project are to develop a simplified aircraft sizing tool, allowing propulsion and system architecture trait studies, as well as to calculate the fuel, battery, and overall masses of the aircraft, to define the wing area and the required thrust, and to analyze the fuel burn, particularly for hybrid electric propulsion system architectures. The tool focuses on propeller-driven aircraft for commuter and regional operation, but can be extended to also support jet aircraft and therefore takes into account Part 23 and Part 25 airworthiness standards. The initial sizing methodology of hybrid electric general aviation aircraft paper, as well as the textbooks Airplane Design, Preliminary Sizing of Airplanes, and Aircraft Design, a Conceptual Approach, were the main references for the development of this tool. On the left-hand side, we can see the major inputs required by the tool. There are, among others, the aircraft type, the engine type, the number of engines, the payload, the cruise range, the cruise speed, the cruise altitude, the temperature of the air, the aspect ratio, the skin friction coefficient, and the far part to be adhered to, 23, 25, or 23 commuter. On the right-hand side, the outputs are listed: the maximum takeoff weight, the wing loading, the power-to-weight or the thrust-to-weight ratio, depending on the type of the aircraft, and the fuel and battery masses. Here, we can see the flowchart of the hybrid electric sizing tool. The three major steps undertaken by the tool are initialization, constraint diagram, and mission analysis. They'll be covered more in details throughout the presentation. The user inputs are considered for the aircraft characteristics. From them, the aerodynamic characteristics are calculated, such as the drag polar and the drag with different flap configurations. In step 1, the empty weight, the fuel weight, and the overall weight are estimated. The thrust-specific fuel consumption, or TSFC, is determined based on the engine subtype: pure turbojet, low bypass or high bypass turbofan, or turboprop. The fuel fraction is estimated based on the range to be covered by the airplane and based on historical data. The empty fraction is estimated based on historical data and the type of aircraft considered. A guess maximum takeoff weight is chosen. Considering all these parameters, the overall weight is then calculated. If the guess and the calculated weight coincide, the mTau is determined. If not, the iterations continue. On the graph, we can see an example of the guessed maximum takeoff weights and the calculated weights and where these values intersect to determine the actual takeoff weight of the aircraft. Moving on to step 2. In step 2, the calculated aerodynamic characteristics are used in determining the flight constraints. The FAR 23, FAR 23 commuter, and FAR 25 requirements are also taken into account depending on the plane considered. It is also in step 2 that an optimal theoretical hybridization of power is calculated. Based on the constraints calculated, the constraint diagram plot is output. The aircraft design is driven by ensuring compliance to certain minimum requirements or constraints for each phase of flight. These constraints, represented by the lines seen on the graph, drive aircraft design and help identify an optimum design point to meet aircraft requirements. Here, the different constraints for the different flight segments are shown. We can see the constraints for stall speed in light blue, for takeoff in red, for cruise in dark blue, and several constraints for climb. The constraints were calculated based on the definitions in Roskamp's Preliminary Sizing of Airplanes book. The hybridization of power was defined using Finger's initial sizing methodology. Above the design line, the dashed line we can see here, the conventional design space can be seen. The hybrid electric space is indicated by the gray area. In his paper, Finger considers the case in which the aircraft is flying the cruise part of the mission only on the power of an internal combustion engine, as it is considered to be more efficient. This leaves us with the green area to choose a design point from. The hybridization of power of the aircraft is defined as the ratio of the power coming from the electric motor to the total power. Assuming that each engine from a same type outputs the same amount of power as the other engines of its type, this equation can be derived, where the critical EM is defined as 1 over the number of electric motors and the critical ICE is defined as 1 over the number of internal combustion engines. A design point is to be selected. A design point on the design line represents a conventional aircraft, like the point here. A design point on the x-axis represents a fully electric aircraft, like the point here. And a design point in between is a combination of electric and conventional power. We can see 2 examples here. Other than the flight segment's constraints, the constraint that is worth mentioning is the one-engine inoperative constraint. If the electric motor fails, the ICE should be large enough to support the aircraft. This is shown by the lower red line. If a design point is selected below the low line, the ICE would not be powerful enough to support the plane in case of an electric motor failure. On the other hand, if the electric combustion engine fails, the electric motor should be large enough to support the aircraft. This is represented by the higher red line here. If a design point is selected above that line, the electric motor would not be powerful enough to support the plane in case of an internal combustion engine failure. This leaves us with the design space represented in gray here. Moving on to step 3. In step 3, an analysis of the mission to be performed by the aircraft is done. In the mission analysis, the energy variable in each flight segment is being solved for. The energy step equation used to do so can be seen at the top. The main variables are taken from the user input. Then the delta energy is calculated, and from it the hybridization of energy is calculated, where the hybridization of energy parameter HE is the ratio of the required transport energy delivered by batteries to the total transport energy. The energy is split in consumable, the energy coming from the fuel, and non-consumable, the energy coming from the batteries. Then the power necessary and the fuel and battery masses are calculated. At the end, the overall aircraft mass is calculated and fed back to restart the loop for the next flight segment. When the loop has been performed, for every flight segment, the overall mass of the aircraft and the mass of fuel and battery needed to fulfill its mission can be determined. To summarize, the tool starts by performing a conventional sizing and weight estimation, taking into account the 423, 23 commuter, and 25 requirements based on the type of the aircraft. The hybrid electric sizing tool outputs a fuel mass, battery mass, and overall mass. The hybrid electric sizing and estimation is based on the desired degree of hybridization. Finally, an energy-based mission analysis is performed to determine the mission performance of conventional hybrid electric aircraft. I'd like to thank my supervisor, Dr. Liscouët-Hanke, as well as the members of the Aircraft Systems Lab for their support during the work on this project. Thank you for listening.